Thank you very much. I'm going to talk about the Maranguoni convection in a floating droplet. After a short introduction, I'll describe the approximations that we use. That's actually the thin film approximation, some theoretical predictions, and some results of numerical simulations. The droplets are ubiquitous in microfluidics, in chemical engineering, everywhere. And if there is some heat or mass transfer, then definitely Maranguoni convection takes place. Historically, the starting of the influence of the Maranguoni effect on droplets was started with the droplets surrounded by an immiscible liquids. The paper of Young, Goldstein, and Bloch is well known. They found the possibility of levitation of a droplet due to the action of the Maranguoni stresses. It is less known that actually the action of the temperature gradient on a droplet was studied several years before that by Fedosov, but he published his work in a certain physico-chemical journal, and this work was unnoticed by experts in fluid dynamics. There's a lot of papers on this subject. I'd like to mention also the paper of Rednikov and others, where the active motion, the self-propulsion of droplets was under the action of solute-capillary effect in the presence of chemical reaction was studied. Again, this problem was first studied, and some results were obtained by Ryazantsev and Golovin several years before that. There is some literature on the droplet in channels. After the seminal work of Dejean, there was a huge amount of works devoted to the droplets on a solid substrate. This is a very non-trivial problem, and it's for explanation of the effects related to the motion of the droplet on a solid substrate, like violation of the non-slip conditions, existence or non-existence of the precursor, dynamical contact angle, difference between advancing and receding contact angles, and so on. Surprisingly, the droplet on the liquid substrate, despite numerous applications, is much less studied, especially in the case of thermocapillary convection. There is a very good work of Greco and Grigoriev, where the action of the gradient, temperature gradient parallel to the surface was applied in the case when the droplet is mostly immersed inside the immiscible liquid and a little bit touches the surface. There are some experiments. First of all, experiments on manipulations on droplets situated on the surface of floating on the surface of a liquid. Mostly my means of manipulation by means of laser heating, and this heating that leads not only to motion of droplet, which can be both in direction of hot and in direction of cold regions, depending on situations. And also one observed in this case some instabilities, some oscillations of droplet, in some cases even splitting of droplets into pieces. And another group of rocks is about the Maranguoni convection in droplets caused by evaporation. Okay, so what is our goal? So we consider a droplet sandwiched, droplet of liquid 2 sandwiched between two media, two fluids, 1 and 3. This problem looks much simpler than the problem of the motion of the droplets on the solid substrate, because actually the problem of contact angles in the triple line was solved in 19th century. That is just a balance of 3 surface tensions of liquids. All the surface tensions are measurable. It's no such strong things like surface tension of the solid. This situation, which is shown on this figure, is sometimes called partial wetting. And there are conditions for the existence of this balance of capillary stresses. There are 3 conditions, of course, but the most important condition is the condition of a negative spreading coefficient. If this condition is violated, then the droplet cannot exist. The liquid starts to move and cover the interface between media 1 and 3 by a certain film. And the results depends actually on intermolecular interaction in thin film, in the disjoining pressure. Depending on the sign of the joining pressure, on some details of this intermolecular interaction, there could be 2 possibilities. One possibility is this, that the droplet is completely destroyed. This is so-called wetting transition. And it becomes just a layer between two media, because in this case, energy decreases. Another possibility is, however, that there is a phenomenon which is called pseudo-partial wetting. And because of disjoining pressure, the most energetically profitable situation is when there appears a thin film of fluid 2 between media 1 and 3, which effectively acts as some interface with smaller surface tension. So this consideration is also possible. From the point of view of macroscope, the cases of partial wetting and pseudo-partial wetting actually are not distinguishable. And this is the way to simplify the problem. Because the problem, of course, the original problem is very difficult. Unknown boundaries, unknown shape of triple line, and three-dimensional flow. So essential simplification can be that if we, in both cases, partial and pseudo-partial wettings, apply this situation, we introduce a real or artificial disjoining pressure in such a way that the second layer doesn't completely disappear. It becomes very thin and doesn't act on anything else. And this idea was first applied, I guess, by Craster and Matar. It was applied in a number of rocks, like Halsky, Pototsky, and others. That's what we are going to do. So we will consider a droplet as a two-layer system. A droplet and thin precursor, and that allows us to use the same equations everywhere. Another simplification is a so-called lubrication approximation. Assume that our droplet is very flat, that the size in the direction of across the droplet is small with respect to the diameter of the droplet, and the characteristic deformation, the size of horizontal deformations is large. In this case, the problem can be drastically simplified because the fields of pressure, velocity, and temperature are just enslaved to deformation. So we can calculate the flow flux, which is caused by a gradient of pressures and also by thermocapillary pressures on the interfaces, thermocapillary stresses on the interfaces, and we can just calculate them. The pressure will include capillary pressure, hydrostatic pressure, and disjoining pressure that I mentioned. The equations will be just conservation of the fluid. Before writing the equations, I would like to mention the Maranguoni, the non-dimensional parameters of the problem. We disregard the gas phase and consider the heat conditions on that phase, on that interface by means of phenomenological Bayer number. Other parameters of this problem are ratios of physical parameters of the systems. Also, there is a parameter which is we will heat or cool some solid body below the liquid substrate. And the non-dimensional difference between the temperature of that solid substrate below the liquid layer and the temperature of the gas is a parameter which I will call Maranguoni number, so it's not really a Maranguoni number, its definition is different. And also parameter is the gravity, non-dimensional gravity is bond number. This is our equations. The equations have been written. These are expressions for the flow rates. Some mobility coefficients and gradients of pressure. This is a part of the flow rates which is determined by pressures. Another part, the disjoining pressure is taken into account only in the precursor, only in the thin film. And we take such a form that we take from the paper of Ototsky and others. What is important is that this pressure, this expression for the joining pressure, allows a thin field, stable thin field. Another contribution to the flow rates is due to the heating or cooling of the system. And after some simplifications, I've converted in such a way, and written in such a way. And that is our formulation. First, let us consider a stationary block. If there is no gravity and no heating, it is obvious that the shape of each interface is just a sphere. In the long wave approximation, the sphere is a paraboloid because any surface near the maximum is a paraboloid. And we can calculate this shape of this paraboloid and find the ratio between the angles. And this is what we see in numerics. It is determined, this ratio is determined by the ratio of the surface tension because it is just the balance of thermocapillary stresses. Here is numerics, which we take some initial conditions, which are Gaussian shape, and it itself becomes a paraboloid. Here it is not completely finished below because it is very slow when the substrate is thin. So that's what happens in the case of when there is no heat. If we heat, we find that we observe that the shape of the droplet is drastic. To explain this change, let us consider, maybe not completely physical, but actually a realizable case when this parameter, the product of Biot number and Maranguoni number is like. In this case, the contribution of the thermocapillary effect into the flow rate prevails. And if it prevails, if we can take this limit expression, we see that for balance, we have to have the constant ratio of the thicknesses, completely different criterion. And that's what we see. The droplet, you understand that it is actually not so steep. It is long wave approach. So it is actually very long and flat. But they are deformed in the same direction. The meaning of this condition is very simple. The system tries to make the distribution of temperature on this boundary as homogeneous as possible to diminish the thermocapillary flow. And that happens in this long wave approximation just when the ratio, the ratios of these two thicknesses is constant. This is what we see in 3D. Indeed, both surfaces are deformed in the same direction. The gravity certainly makes the droplet much more flat, even more flat. It is very flat, except the regions near the triple line. If we heat it weakly and from below, and I will explain why we cannot heat it strongly from below in a few minutes, and then nothing changes. But if we heat it strongly, we again see the deformation of both boundaries of the droplet into the same direction, and the difference is a very flat interface. Okay, now I want to talk something about non-stationary droplet, and actually the droplet can be unstable. At present, we have no self-consistent theory of the stability of the droplet, but because the droplet is very flat, the results on the stability of layers can be useful, because flat droplets are actually layers, but they have some boundaries. And in the case of layers, there are two kinds of instabilities. One kind of instability is monotonic. It is a usual Maranguoni deformational Maranguoni instability of Scriven and Sterling with a threshold proportional to your number. And oscillatory instability is because we have two layers. Two layers can be oscillatory stable, it is known. Is it instability depending on the parameters of the fluid can be by heating from below or from above, but it is by heating from below, it competes with monotonic instability, and monotonic instability usually wins. But if we heat from above, for some interval of your numbers, larger is some critical and smaller some other value, there are instabilities in layers. And indeed, we observe instability in droplets, but of course now it's characterized not by the wave number, but by azimuthal wave number. This is an example of instability with azimuthal wave number 1. This is two upper boundary and lower boundary of the droplet at some time instant, and this is after half a period. With the growth of Maranguoni, we can get some more exotic shapes. There appear some hole inside the droplet due to the intensive convection, and even the droplet can be splitted. But I will not discuss it. I will consider now the case, what happens when we heat the droplet non-homogeneously, when there is not only vertical, but also horizontal component of the temperature. It turns out it's quite natural. Okay, so we first obtain droplet without this modulation of Maranguoni number. And then we apply this modulation. In the left part of this region, it is colder, and the right part, it is hotter. We see that under the action of the surface tension, the liquid in the droplet moves to the cold direction, and we see here that there is a lot of fluid in the left-hand side and much less in the right-hand side. This motion continues, and we see that there is something like a satellite starts to appear, because in the thin part of the droplet, the motion is slower, and this liquid cannot move sufficiently fast. Indeed, we get some satellite, but at large values of temperature, this satellite starts to decay, and finally we don't see it. It doesn't disappear completely, but with this discrete visualization, you don't see it at all. Because the substrate is liquid itself, it also is subject to the thermocapillary convection. In the cold, the substrate layer is cold in the region of the substrate is thicker in the region. Sorry, it is a region of, that's what we see, that it is a little bit thicker in the cold region. If we have a gravity, essentially we get the same. With the droplet initially is much more flat, it is still much more flat, but again, the liquid moves into the cold part of the droplet. Some hole appear, and then it disappears, and also actually both bounds of the substrate become thick. Okay, I didn't show the case of heating from below. That is a monotonic instability, and for monotonic instability, as I told, the instability of substrate itself appears, and the droplet acts as a seed for this instability, as it's a finite amplitude disturbance, and finally the surface droplet is destroyed. Okay, so these are my conclusions. We have seen the changes of the shape of the droplet due to the Maranguoni convection. And we have seen that the droplet can be unstable, actually monotonically or oscillatory, and also quite predictable motion in the case of inhomogeneous. Thank you for your attention.
Okay, thank you very much for very interesting talk. Questions, please.
Can we ask the question?
Please, okay.
Dear Alexander, your calculation relates with non-dimensional parameters. And what can you say about the characteristics of this drop for real physical parameters?
Okay, because we consider there are two kinds of instabilities, of Maranguoni instabilities. Pearson instability, which is not related with the deformation of the boundary. It is cellular cells which appear, and the unstable this deformation instabilities takes place only for very thin film. So this should be a very thin film, such thin film that the threshold of, for usual Maranguoni number, the threshold is about Galileo number. And for only for very thin film, smaller than millimeters, tens, hundreds, micrometers, this instability which is considered here prevails. Otherwise, you have to consider the full three-dimensional instabilities, because it is only for long wave instability.
I have a very short question. I have a very short question. First of all, thank you for a very nice talk, Professor Nepomnyaschy. And the question is this: there are Kabov's experiments which do you have some maybe qualitative comparison with some experimental works, in particular with Kabov experiments? I believe that he has similar with your topic, experimental.
Well, the effects are similar, but the real experiments, in the real experiments, one cannot ignore the Rayleigh convection. And there's only buoyancy convection. The buoyancy convection is together with Maranguoni convection. But so if would we solve a real three-dimensional problem by DNS, we would definitely include the Rayleigh convection. But here, in the case when not Rayleigh, not Grasgoff, but Galileo number is of order of 1, we at this limit corresponds to very, very small Rayleigh number, because Grasgoff number is Galileo number multiplied by this coefficient of Gaussian-esque approximation beta t, which is assumed small. So this theory is valid for much thinner films than are in experiments, because that's the instability that we consider is only for very thin fields. It's what we can do by long wave approximation.
Okay, thank you.
Okay, we could have time for one more question.
Can I ask?
Okay, I see here a question in chat. Can a droplet disintegrate into several droplets in the problem you are considering? Yes. I didn't show that, but we indeed, with the growth of the Maranguoni number, we observed first some transitions. These oscillations that I showed are in the very beginning. Then we got some transition oscillations of other kind with a certain hole inside the droplet. And for larger values, we see that the droplet can be disintegrated.
Okay, and there was Igor Wirtgame wished to give question.
Yes, it seems to me a good idea to imagine the droplet as two waves with deformed surfaces. But in the case of absence of gravity and heating, why the deformation was in the surface?
It is well known that in the case of no heating and no
Gravity.
Gravity, the droplets wants to minimize its surface.
So it's simply due to capillary.
Capillary, yeah.
But you consider the infinite layer and droplet on one place of this surface. In which place it's possible?
Okay. This is our approach. We do not distinguish between partial wetting and pseudo-partial wetting. Our model is like that. We have a droplet, and here there are some people, for instance, Starov says that the precursor always exists. Some people say no, it not always exists. For us, it is for our calculations. It is, of course, it is important, but not for our calculations. For our calculations, if it exists, that is real precursor. If it does not exist, it is artificial way for calculations. And then you can look on the shape of the droplet. And in the paper of Kraster and Matar, it is written how to make how to choose this artificial disjoining pressure in order to get real angles. And that's what we get in actually in the case. This is actually
so the droplet is artificially put into this.
So we don't know. Some people think that this is not artificial, that it is real always. Some people say that no, this is artificial in the case of partial wetting, and there is pseudo-partial wetting where that is real. Okay, we don't. We are waiting for experiments that will check whether this thin layer really exists.
Okay.
Thank you very much.
Thank you very much. We do not have time for further questions, unfortunately.